So this is the video for introduction to section 3.10, which is the related rates. So what are related rates good for? Related rates are basically, and scientists use related rates to try to connect rate of change of one thing to another thing, and if they are connected to each other. And so in general, we have been studying problems where one quantity is changing and then the other quantity is related to that one quantity. And so, for example, area and circumference of a circle are related to each other. Radius, surface area, and volume of a sphere are related to each other. Height of a kite, length of its chord, and angle of elevation of the kite are related to each other, and so on and so forth. And so if two quantities are related, then so are their rate of change. So let's start with iClicker question 1. In section 3.10, a deli clerk slices a log of pepperoni so that its length L decreases at a rate of 2 inches per minute, and the total weight W of pepperoni has been cut increases at a rate of 0.2 pounds per minute. So the pepperoni weights and all these options on pounds per inches. And so I suggest take a pause and think about the problem for a minute and answer the question. Okay, I hope you paused. And now let's try to solve the problem. So first thing is that it tells you that the pepperoni is changing by 0.2 pounds per minute, 0.2 pounds per minute. And then also, and this one is, and then the change is the amount that is being cut is changing that much. And the amount that is being cut is at the rate of 2 inches per minute. So if I basically, it feels like these two are going to relate to basically how much weight per inches pepperoni has, and it seems like it's 0.2 pounds per 2 inches. That is 0.1 pounds per inches. And so now, and also if you look at the units, you can see that they simplify, minutes and minutes simplify, and you end up with pounds over inches. And so the answer is B. This should give you a little bit of an insight on how we do the related rates. Again, rate of change in inches per minute and then pounds per minute sort of related to how many pounds per inches we have. So the two rates of change were related somehow. Now let's do iClicker question 2. Suppose y is equal to 5x squared and dx over dt. Our rate of change of x with respect to time is equal to 3. When x is equal to 2, what is the value of dy dt, or rate of change of y with respect to time? And it gives you a few options. I suggest pausing and thinking about this and then coming back and watching my solution. So I hope your pause was helpful. Now let's try to solve this. So in the previous problem, we were just relating things, how it felt natural. Now they give us rules of the function, basically. And so this is how the my variables are related to each other. Y is equal to 5x squared. And I'm trying to find the rate of change with respect to time. And it seems both x and y are changing. And so this time I'm going to take the derivative of both sides, and I end up y is a function of time. So I have this, and then x is a function of time. Both of these are functions of time. And so I will have outside function is 5x squared. So I will have 10x. Then derivative of inside is just dx dt. Now, now that I have this, let's see what values do I know. I know that x is, I'm evaluating at the time that x is 2, and I also know that at that time the rate of change is 3. So I multiply them all together, and I get the answer 2 times 3 times 10, which is 60. So we already done 2 iClickers on this type of questions. Now we're trying to figure out how, in general, we set these things up. Let's say a cube has sides length x, and all sides are growing at the same rate. How fast is the volume V and the surface area A changing? And of course we want to see if they are any and they are related at all or not. And so what's the formula? First of all, I know both volume and surface area are related to this side of the cube. Basically, surface area is there are 4 squares in the cube and 6 squares in the cube that are the surfaces of the cube. And so you have to find the area of each and multiply by 6. For volume, you just multiply width times height times the length, basically, and that's all of them are the same, and so it's x to the power 3. Now, if I take the implicit differentiation of the volume, what do I get? I get this one. I get derivative of the volume with respect to time is equal to, outside function is x to the power 3, so it's 3x squared dx over dt. And inside function is x. How do I find the implicit, when I do the implicit differentiation, how do I find the derivative of area or surface area? Then that would be again dA dt is equal to derivative of this side is 12 times x, and then derivative of inside, which is dx dt. Now, if I'm looking at these two, I actually see that the two of them are related. How are they related? If I let's say divide dv dt over dA dt, then I'll get 3x squared dx dt over 12x dx dt. And then I can say, oh, let's basically simplify dx dt over here, and then simplify these. So this would be 1, this would be 4, and that goes away, and then I end up with x divided by 4. So v prime is equal to a prime times x over 4. Now I can answer this question. Now that I have this v prime over a prime is equal to x over 4, I can answer this question. If the volume is increasing at 4 cubic centimeter per second, how fast is the surface area increasing when the cube is 200 centimeter on each side. So this is asking me, this is giving me, what is it giving me? It's giving me volume, the rate of change in volume. So it's giving me dV over dt is 4 cubic centimeter over second. And then it's also giving me 200. What's that 200? 200 is the x. So basically I have 4 divided by a prime is equal to 200 divided by 4, and this way I can calculate the value of a prime by and would be a prime is equal to 16 divided by 200. That is the rate of change in surface area is 2 divided by 25 square centimeter per second. Another problem. A rectangle currently has length L equal to 16 feet and width W equal to 8 feet. The length is increasing at rate of 3 feet per second, and the width is decreasing at rate 2 feet per second. So I have at the instant that we're talking about, L is 16, W is 8. What is dL dt? dL dt is equal to 3. What is dW dt? That is equal to -2. So these are feet per second. Same thing here. Okay, so I know all of that, and what the first part of the question is asking is how fast is the perimeter changing? So I know the rate of change for length and width, and we're trying to figure out the rate of change for perimeter. What we need to do is to relate perimeter to length and width. How do I do that? Let's draw this. Length, width. And so the perimeter is going to be equal to 2W plus 2L. Now, that's the first step. We connected, well, that's the step that we connect the variables together. Now we have to take the derivative of both sides. With respect to what? We're trying to find the rate of change in here with respect to time. And please remember, it's not always rate of change with respect to time. But a lot of times in physics and in a lot of areas of science and also business, you're trying to find the rate of change with respect to time. And so here I'm gonna try P derivative of P with respect to time is equal to 2 is the constant. Derivative of W other function is just there's no composition going on in there, so it's dW. There's no trivial composition going on in there, and so now it's 2. Again, no trivial composition, so I get this. Now, how do I find? My goal is to find the rate of change in the how fast perimeter is changing. So I have to plug in the values that I have. For this one, I have -2. For that one, I have 3. So it would be -4 plus 6 equal to 2 feet per second. That's the rate of change, and that's how fast the perimeter is changing. Now let's try to find out how fast is the area changing. And to find that out, let's set up the area function. I want to relate area to length and width. Again, this is the picture. Let's say this is length, this is width. It doesn't matter which one's bigger at this point. And then I say A is equal to W times L, right? As one side times the other. Then when I take the derivative with respect to time, it would be a product rule, derivative of the first one, again respect to time, times L plus first one times the derivative of the second one with respect to time. Now, we figured out dW, the width is decreasing at rate 2, which is, this is negative 2, and the length is equal to 16, and then width is at that instant equal to 8, and L is increasing at the rate 3. And so relating the variable that we're looking for, its rate of change, to the other two variables that we knew the rate of change, now it's giving us a chance to actually calculate dA dt, which is in here is going to be negative 32 plus 24, and that is negative 8, and its change in area over time, which is going to be feet squared divided by second. So what we've seen so far in solving related rate problems, first if it's applicable, we should draw one or more figures representing this situation. And then we want to identify the quantity in the problem and figure out which ones are constant, which ones are variables, which ones, and then we want to figure out which one are which rate of change is known, which rate of change is asked, like in the problem that we just did. All the rate of change for length and width were given, but we were asking for the rate of change in parameter and area. And then we want to find an equation which relates these quantities together. And then these equations are often geometric, especially in calculus when we discuss them. In other areas, like in business, they may not be quite geometric, but it might, you may see other applications in there. And then you differentiate the equations implicitly, and then you substitute the known quantities and the rate of change, and you'll find the rate of change that the problem is asking you to find. Okay, so now let's try to do our first formal example. This example is asking, oil is leaking from a hole in the ocean floor, forming a circular oil slick whose area is increasing at a constant rate, 5 kilometers squared per day. How fast is the radius of oil slick is increasing when the area is 100 square kilometer. Okay, so something to mention. This is an actual problem that would happen. So let's say that they know that they have an oil leak, and they know how much oil is being lost, so they can figure out how fast the area is increasing, and they just want to know when the oil slick is going to get to their shores, because that can be determined by the radius. So that's what they want to do, and take some preventative measures basically. So now let's see, what are the information that we have? I told you a little bit of stories. Sometimes this little bit of stories help a little bit in getting you interested, or these are real problems that we're going to face in our future. And so forming, hopefully not this one specifically, but some of similar questions are going to be of your concern in the future. And so we're thinking about a circle, and so we want to know how the area of the circle is related to the radius. And we kind of know that, don't we? That is pi r squared, right? Let's keep this apart. What are the variables that I'm looking for? Or what do I have? What am I looking for? What is changing? In here, I know radius is changing. So radius is changing. In fact, the question is asking how fast is the radius changing? And so that is a variable. And that's the question that this question is asking. And then the other part that I know is that it's telling me that the area is increasing at what rate? It's increasing at 5 kilometers squared per day. Now, let's just keep all the information that we have and try to take the derivative of both sides, see how the change in area is related to change in radius. When I do that, I see dA dt is equal to, it's pi times 2r, which is 2 pi r, and then derivative of inside r squared, inside is r, dr dt. So let's see what I need. I need dr, and to be able to connect dr dt to dA dt, I still need to have an r in here. I do know this amount, which is 5. I just need to figure this one out. And so how do I figure this one out? There was one piece of information that I didn't quite use up there. It tells you that at the point that the area is 100 square kilometer. And so if I use that, would I be able to find r at that instant? Yes, I'm going to use this formula twice, once to take the derivative, once to find r. And so I'm going to set it 100 is equal to pi r squared, and that gives me r is equal to square root of 100 divided by pi. That is 10 over square root of pi. Now, let's plug that back in here. So I get r is equal to 10 divided by square root of pi, and then I find dr over dt, which is going to give me, this is 20 times pi divided by square root of pi, and I have to go reciprocal, multiply it by 5, so I get 5 square root of pi over 20 pi, which is going to simplify to I can put the square root in the bottom, or I can take it upstairs. Either way will give me, if I can change color, I'll tell you, it's going to give me 1 over 4 square root of pi. And what is the units for this? That's kilometer per day. Okay, so again, let's look at this problem a little bit further. And so when we were solving, basically we got to this point that we said r prime is equal to a prime divided by 2 pi r. And this is when we took the derivative, and then we figured out dA dt is equal to, dr dt times 2 pi r is equal to dA dt. If you solve, you get it this way. If you look at this, as r grows, r prime is going to get smaller and smaller. When this gets bigger, this one becomes smaller and smaller, which is hopefully a situation. If a prime stays the same, then as this gets bigger, this gets smaller, which is normally when the oil slick in the beginning, it grows really faster and then starts growing slower and slower, basically. That's interesting fact to know.